me start. I'm sure we'll have some people coming in and out as we go along. So firstly, thank you for attending my talk. So today I was going to talk about storage controllers and what adding Linux to them can achieve and how to do that cost effectively. I'm Neil Werdmuller and I work at ARM. I'm assuming most people know ARM, but we're fundamentally a processor company. We don't make chips. We make processor technology that we sell to other people that make chips with it. I'm assuming most of you have, with all your smartphones, you've got lots of ARM technology about your person today. So there's also a lot of that ARM technology goes into storage. Some of the benefits of ARM there are because it's small, low power, and readily available. You know, the ARM business model is everyone used to develop their own processors, huge teams, everyone going along doing their own thing. ARM develops them and then sells them multiple times. It's more a cost-effective work model. Now, of course, there are other processor companies, guys like RISC-V coming up. So we're not the only game in town, but we'll give you the ARM perspective today. So I was going to go through and give a little overview of the typical storage controller architectures. Very, very brief overview of computational storage, because I suspect a lot of you may have had this 4 times already today, but some of you may be new to the topic, so I will just cover it briefly. Get into an overview really of some of the computational storage drives, or CSDs as they're defined by the SNEER twig. And then some of the discussion around benefits of having Linux on the drive. Now, a lot of people might think, well, Linux on a drive, it's crazy. But hopefully I'll lead you through the thinking behind it and why we think it makes sense. And why a number of our partners have already done drives like this. So you heard from Scott, NGD earlier this morning. They are shipping an ASIC that runs Linux on the storage. So the compute in an SSD is interesting. So typically it's broken into a front end, host interface control, and the flash translation layer. The flash translation layer is really about mapping the blocks onto where the little pieces are stored in NAND. So basically when you get a request that comes in over PCIe, you've got an NVMe command, so you've got to unwrap the PCIe, you unwrap the NVMe. Then this system here, the flash translation layer, will create descriptors to send to the back end. And that back end will start pulling out all the pieces, putting it in, assembling it in the RAM. Then it can signal back to the host that it's available and DMA it back again. The back-end processors are often in the same SoC, but typically it's a separate processor, so you can have a lot of parallelism. Quite a few of the systems today have 16 NAND channels, some have 32. There's an interesting dynamic with this, because these NAND channels need about 20 pins per channel. When you're getting down into some of the smaller nodes, like 7 nanometers, if you've got 32 NAND channels, all of having 20 pins, what you find is the chip becomes I/O bound. What that means is it's the pins on the bottom of the chip that decide how big it is. So you don't want to waste any area. You're paying for the silicon. So if you get to that position, then actually you may have spare silicon in there where you can put compute. Now, it could be an ARM processor or any other general purpose processor. It could be an accelerator hardware. It could be FPGA. There's many things that you could fit into that. But it's an interesting dynamic now that the pins are sort of directing the size. And that's obviously going to get, as you get even lower and smaller nodes, it's going to become the same. Interestingly, a tape out to do a mask set for a 7 nanometer, somewhere between $10 and $14 million. So you want to make sure you get that right. But yeah.
At least the second time.
At least the second time, yes. Another interesting dynamic, roughly, and it varies depending on people's technology, how they manage a flash translation layer, but roughly it's 1 gigabyte of RAM required in the drive per terabyte. Now, That's primarily when you've got the flash translation tables here. There are other technologies where you're trying to reduce this RAM by using the host RAM. Fundamentally, that flash translation layer has to live in somebody's RAM, somewhere. In many cases, in a typical SSD today, it does live on that drive. Clearly, lots of different interfaces, but yeah, PCIe, NVMe seem to be the really big thing. There are often, though, compression engines inside, and there's always going to be almost always encryption, parity check, low-density parity checking. But there's also, quite often, you can have machine learning, FPGA, other things that are already embedded in these devices. Really, I won't go through all of the SNEER definitions here, but really what this is really focusing on is a programmable computational storage device, where you can change that code. So, very brief introduction to computational storage and its mission. So this is a traditional model where basically a server will sit here, it'll make a request to the storage. The storage will go off and find it all in NAND and move it into the cache and then send it back up again. It can then do its compute. There's a lot of evidence that a lot of servers sit there waiting for something to compute. You know, if you do a read and you're waiting for that data to be able to compute the next thing, you've got to wait for all of this to happen. So often it gets stalled. Now, if you've got multiple threads or you can switch threads, there are ways that people work around it. But fundamentally, the utilization often of servers is not great. It also obviously adds latency if you're moving this around. And now this could just be a PCIe connection. This could be NVMe over Fabric. It could be NVMe over TCP over a wide, very long distance. So some of this can be slow. And often if you're going through an infrastructure as well, you've got lots of buffering, lots of copying all the way through. And this is all consuming power, adding latency through that system.
You said can be slow. You mean latency? You mean throughput?
I guess latency would be, is the term. So the latencies get delayed. Every time you have to buffer it or it's getting stored, then it's a latency issue. Yeah. In layman's term, it's slow. But it's expensive. There's power in all these pieces that the system's going through. And I think some of the others have said today about the explosion of IoT and how you're just going to have to move processing to the edge. So the idea behind computational storage drive is really that you have compute on the drive. So the server, whatever wants its operation, can make the request. It happens on the drive, and you return the result. There are other cases where maybe this compute is just happening. Things are storing, perhaps images are being stored to that drive continually. Typically, say if it's say it's a security IP camera, and this is basically just storing data to the drive. In the classic model, to search that security data for movement, maybe using an ML engine, you've got to move that video stream to the server. Obviously taking huge amounts of bandwidth to do that. If you run the ML on the drive as that data is being stored, basically you can just say, if there is an alarm, you just send the alarm up. You don't need to be transferring all that data. You could be having a lot of sensors, so maybe smart meters are sending data. This is sitting on the edge, your storage device. It doesn't necessarily need to send data all the time. It can just consolidate it, maybe send a big packet of the latest ones or send data that's looking unusual. There are a lot of applications here. Now, and I don't think any of us are claiming this is replacing the traditional storage. There will be, for many years to come, there will be heaps of Xeon servers with lots of storage in data centers. But there are some really interesting and novel applications, I think, of computational storage. I think some people look at this and say, whoa, you're competing with what's around today. No, this is new, it's exciting. You can do lots of different things with it. So obviously here, the benefits here is you're not having to do so much wrapping of protocols all around this. So typically, if you're retrieving the data from the NAND, you move it into RAM, then you can operate on it. You don't have to move it into RAM, then wrap it in PCIe, wrap it in NVMe, and move it across. You can just move it straight to NAND and then process it. We touched on as well that really security. This can have security benefits because really not all of that data is being shifted away from the drive. A lot of it just happens on that drive that can be secure. So, as I said, I see this as an evolution in many cases along the interfaces. So today, your average SSD drive with a PCIe and NVMe looks something like this. You've got your front end, your back end processors, your RAM, and a PCIe interface. There are also, if you're using NVMe over Fabric, again, then you could have either Ethernet or any other Fabric interface on the front here. And basically, you're getting NVMe packets over a different fabric, but fundamentally, you're getting NVMe packets here that the front end operates on and does what it's asked to do over NVMe. There is a third version, which is primarily what I'm going to talk about today. As I say, it's kind of a superset of everything before it. But actually, if you're running Linux on this drive, fundamentally, this just appears to be a server. You've got compute, you've got RAM, and you've got storage, and it's networked. So I think that's a really novel, there's a lot of applications there. A lot of them haven't been designed yet. It's a very low-powered server, but it has got that storage right next to it, and there are a lot of interesting applications. So really, yeah, as I say, we start with the standard PCIe NVMe SSD, and what comes over here are PCIe messages which are encapsulating NVMe. Once we move to NVMe over Fabric, and for example, I've used TCP, what you're getting is, over the Ethernet interface, is you're getting TCP IP packets that are encapsulating the NVMe. What's interesting in this third example, though, is if you're getting Ethernet packets, and some of them, you can use it as a traditional NVMe over Fabric TCP drive, because you'll be getting those TCP packets encapsulating the NVMe. But also, you can just be receiving standard TCP IP packets as though it were any other server. The NVMe over Fabric, those will just be sent straight through the front-end processor. It doesn't have to be in the data path at all, so that will just operate as a standard drive. But if this Linux processor just intercepts these standard TCP IP packets, effectively you've just got Linux running here, and it can then do what it wants. So it can, if you've got an application running here, a database, it can send NVMe commands to the front end, which can then assemble the data that it wants into the RAM, and then it can just access it here directly. It doesn't need to move it anywhere. So that's, to my mind, is a neat opportunity, because it's not replacing the NVMe over Fabric, but by having this Ethernet, you can basically make this look just like a standard server. So yeah, why Linux? Certainly in the past, we've had people that have developed embedded code, bare metal, or with an RTOS that runs on a drive. And it's good. Quite often they're more fixed function, so that they'll do something and they'll do it well, but very hard to program. You need to know exactly what it is. You need to understand the memory map of the drive. It's complicated. Clearly with Linux, one of the benefits is there's a huge open source community. And as Scott from NGD was saying this morning, if the customer has a new application and it's Linux, and typically it's been running on Intel, they just recompile it to run on ARM. It works. It's very straightforward to move it across. You don't have to reinvent wheels. So, lots of protocols just come for free through the open source community. All of these applications, and there are many good examples of databases, of machine learning, and I'll show how that kind of fits together in the stack a little bit later. But the other area that is very interesting is that if this SSD now just looks like a server, it can be managed like any other server in the system. Now, whether you're downloading workloads using Kubernetes or Docker, whether you're just monitoring it, it can just appear like a standard server. And this could be right at the edge, somewhere very distant from your data center. But you can actually administer it from a long distance away. So you can put these right at the edge of any system. And of course, you've got to be able to have proven tools for debug and development. So it's not impossible to do it any other way. Clearly, you can download FPGA images using a similar function to program accelerators are on the drive. But it's probably good to wrap them up in a Docker container, send them down, and then load that FPGA on the system. So it can be useful for programming other accelerators in the system. So a little bit techie here, but what's required to run Linux? Some of the background here is that typically processors come in at least two flavors. Your classic applications processors, so be they Intel x86 or ARM Cortex-A series, they have what's called a memory management unit. And what this means is that the applications just see a virtualized system of memory. They want some memory. The hardware provides it to them. They don't know where it is, doesn't really matter. It all just works. But it's
Throw in, Linux does not require MMU makes Linux a lot more useful. There is no new Linux with a lot of applications.
That's correct. And there are the used to be UC Linux that's now gone into the kernel mainline. That's correct.
Your mainline, you can run it on ARM2 or Spike, where it just didn't know if you force Spike.
No, I keep saying there are other processors that are available. But what I would say is that a lot of Linux, we've got at ARM a lot of open source guys, hundreds, and they spend a lot of time porting and then optimizing code to run on ARM. Most people do use the MMU system. I think if you went to use the non-MMU system, there would be a lot more rework that you'd have to prove. So these are kind of application processors, and they're typically what's used to run Linux. Now, typically in an SSD, people want very hard deterministic responses. So in a virtualized memory system, things like you may end up with a page table walk that takes a few thousand cycles. Now, a few thousand cycles if you're running at a couple of gig isn't necessarily a lot, but if you're in storage, that will create a delay and you'll get your long tail, which the server guys hate. They want to have it very deterministic. There are ways of creating big pages, trying to avoid page table walks, but these are designed for maximum average performance, whereas real-time systems are designed for very deterministic, knowing exactly what's happening. So typically lower average performance, but very measurable, very deterministic. And the way it does that is when you write your code, you've got tightly coupled to memory that's sort of always available. So an interrupt comes in, you've got code, you know it's there, it hasn't been evicted because you're in control of where it lives. You may have another level of sort of shared SRAM that's in the system, and then you've got the main system, but you're directly addressing all of this. So it's a very deterministic, very low latency, but yeah. You can run Linux on a system like this, but I wouldn't recommend it. Now there's some SSDs that also use application processors for the front end. Majority use Cortex-R series real-time processors for the front end and the back end. So there are quite a few partners that use this on the front end of SSDs. So if you're already using an applications processor in the SSD, you can do this straight away. Clearly with the Linux ecosystem, and here some of these you can go through, Linaro was founded, it's separate to ARM, but it was co-founded with ARM in 2010. And the idea is that we're porting and maintaining Linux distributions and applications that run, to get them running on ARM. There are also a lot of engineers inside ARM. I think in terms of kernel, what's the word? Uploads, upstreaming. Thank you. And I think with a number 3, ARM is a number 3 contributor to upstreaming in the kernel. But there's lots of different things. I'm not going to drag you through all of them. There's also works on ARM that shows some of these things, but as I say, it's there and it works. I would say people were asking about other processors. I think that investment that ARM has been making over these years, other processors out there will catch up, but it does take time. There's a lot of work to get this all working smoothly and then maintained. So as you go through the system, in order to add Linux to the drive, I think there are a number of different approaches. So the obvious one is that you could just add an applications processor onto the PCB of an existing drive. You're then still having to communicate over PCIe, typically, unless you've got a different kind of connection here. In the future, this could be CXL or C6 or something, but typically you'll go PCIe now. Now, obviously here you're going to have to duplicate some RAM because you're going to... So this isn't ideal. You've got a two-chip solution, but there's an obvious evolution where you move it into a single SoC, and now you're sharing that RAM. So you're moving it from NAND into RAM. Now you can process it. There are also other options where if you're using Cortex-A series for the front end, you just can extend it so that you're still using this same system. A lot of concerns we hear, maybe, well, running Linux on a drive. Linux is huge. How's that going to work? Typically, even something like Debian or others, I think Ubuntu wasn't a million miles away from here. But it says that you need, in terms of storage, about 2 gigabytes. Well, if you've got a 16 terabyte drive, that's not a huge problem. Now the RAM, 512 megabytes. Sometimes people recommend up to 2 gigabytes. Yeah, if you've got 16, but hopefully if you've designed your SSD correctly, you're using that 16 for good purpose. But adding another couple of gigabytes or 4 gigabytes, it's not a huge cost adder to this device in order to get Linux running on it. Clearly, you can use very much cut-down Linux versions as well. There's all sorts of variants out there that can reduce the size. You don't need the whole UI system when you're running inside a drive. Slight plug for ARM here, so I apologize for that. But
You can take a break from plugging ARM. Sorry.
yeah, next slide. Yeah. So as I say, Linux on average requires an application. It makes it easier, certainly. In ARM, we do have a huge range from tiny little A5s all the way up to huge A77s. You can have multiple clusters of them. You can have one little one. There's a big range. So one of the challenges with computational storage, if you just want to do a generic drive, is how much performance do I need for my compute? That's a big decision because you need to decide that when you're making your SoC. Do I need 64 A77s or do I need 4 A55s or A53s? Can vary a lot. Something that ARM has inside it is, and it's using Neon, which is a single instruction multiple data, DSP-like capabilities. And that exists in these processors, but it can accelerate ML workloads a lot. Now, you can do hardware ML neural processors as well. ARM has one, but there are many others out there. Or FPGA to do the same thing. But a lot of this ML is already there, and I think ML is one of the great workloads for this. This I'm going to touch on because it's very new. I won't dwell on it too much, but in the past, I think ARM has been seen as inflexible. You've got to license everything up front, huge amounts of money. If you're a startup, you don't want to do it. So I think some of the new entrants in this space are teaching us some lessons, and we're learning from them, and we're trying to be more flexible. So ARM Flexible Access makes it easier, I think, for startups and other companies to innovate and create SoCs quickly and cheaply. So it gives you an access to a huge range of ARM IP. I'll show you a list in a moment. And you get RTL, you get training, you get full support for everything that's in the package, all of that IP. The way it works is a very low entrance fee. It's $75K a year if you want to tape out once, $200K if you want to do multiple tape outs. Then on a tape out, If it happens, it may be years later, or it may not happen. That would be when you would pay a smaller license fee, and then when you ship a small royalty fee. But it's a lower barrier to entry than we used to have. As I say, you get tools and models for all of this. You get lots of ARM IP. You get GPUs, which you could use for ML or other things. You get support and training all in the package. But it includes all of the M series, the smaller processors, all of the current R series, and all of the A series up to A53. Some of the high-value, latest and greatest processors aren't in this package yet. Things will trickle down over time, and more of them. But some of that high-end IP is currently licensed in the old-fashioned way, if you really want the high-end stuff. But this covers at least around about 75% of everything that's ARM's licensed over the last 2 years. And we've got these CPUs, we've got interconnects, we've got GPUs, there's a whole load of security things down here, system controllers calling, and some bits and bobs. Debug is critical to pull this system together. What's nice is that people can experiment now. In the past, you may have had maybe an R5, and you think, well, the R8 would be better, but you don't know until you got it. Here, you can play with it. Anyway, I thought I'd mention that. Also, for educational, for universities and colleges, they can get all of this same thing, but without any charge. So again, that's hoping to seed people to start experimenting and learning with ARM, make it more accessible. So, machine learning. This is one of the, I think, one of the most interesting workloads that for computational storage. The reason being is that you basically have things being stored to the drive all the time. And actually the inference, so using the model that's being generated from training, is usually pretty trivial compute. So something like Neon inside the ARM can really do this very quickly. Depends on the complexity of what you're doing. But even if you're classifying objects in pictures or doing facial recognition, that's all stuff that can happen with machine learning on the drive itself. There's also training. Now, this doesn't solve everything, but sometimes where your training is continually being updated because you're getting new data. So you're storing more and more images and you want to use that to train the system. You can do that each time it's added. There will still be seas of NVIDIA's doing heavy lifting training. I'm not claiming this replaces it, but I think there are some interesting applications where this can work on the storage. Some storage isn't flat out all of the time. Sometimes it's really busy during the day, and at night time it's just sitting there, really. Sometimes you can then use those idle cycles to do machine learning or do other applications in those quiet times because it's on the drive. To fit with this machine learning, basically there's a whole system. So obviously it works with ARM, but it also works with other partner IP. So DSPs, we've worked with NVIDIA to plug into the bottom of this. This all then just works with the ARM compute library, neural networks, but with all the standard ecosystem on the top. There is a compute library. It's available free, no fee. It's an MIT license. But it implements a lot of the basic functions that you need, manipulation of color, convolutions, canny edge, whole range of the standard kind of things that are needed, including the convolutional neural networks. So yeah, quarterly releases. They even runs on some of the tiny Cortex-M processors as well. But as I say, if you want to download it, you just go and help yourself. Yeah, one of the things that I think this is a very early stages of computational storage. And I think people can throw rocks at it from many directions, thinking of specific applications. But what I'm interested in, though, is I think a lot of the people are thinking, well, I'm going to use it to replace what we've got today. I think it opens up many new avenues, new ideas. Some of the early concepts of Ceph, where the drives would all be self-managing or EU social. So that, basically the drives, you throw things at them to store them. It manages all of the sharding and the erasure coding and duplication across a whole range of drives. Now, this is going to require software to be developed that understands this. But fundamentally, because these drives are there, they're running Linux, it opens up a whole range of possibilities. I suspect there'll be a lot of startups jumping on this with many different interesting things to do with it. But fundamentally, at the end of the day, it's an edge server. Very cheap, very low cost. It might fit in a tiny rack. You might just plug it into Ethernet and a power block and stick it somewhere. Fundamentally, it's just a server. But in a classic edge server, you'll plug in an SSD with PCIe and the RAM and you've already got that. It's just a simple, low-cost version. So, and again, we were here last year and at FMS. Last year at FMS there were 4 talks, and then this year there were 19. I think we could have probably doubled that if there'd been more slots. And clearly there's been a full stream here at SDC for a whole day. As we've heard from a number of vendors, these exist today. People are shipping them, people are using them, people are buying them. With the standardization, there is a long way to go, and I do encourage people to get involved with SNEER to do this. Obviously, Jason from ARM, he attends all of the meetings. We're working on it. But I'd like to see it move faster, if anything. I think Linux is a great way. It's not the only way, but it's a simple way that people understand. It can be quite small. It fits in that kind of environment. You could just connect it over NVMe and PCIe. That's great, and you extend maybe the NVMe protocols to support the computational storage. That's great, but then you put it over TCP. Great, then you've got the distance. But then if you've also got just a normal TCP connection to it, it's a server. You can manage it in any way you would anything else. And I think that's really interesting. We've got a white paper. It goes into more detail, free to download. Just go to storage.arm.com. So it's got some examples from some of our partners and goes into a bit more depth. And that's me. Obviously, please feel free to reach out and talk to us. So I've probably been a little bit quick, but I've got some time for some questions.
Well, question and command. So speaking, I'm sure with my Linux kernel hacker hat on or my Attendees standards group member hat on, once we remove the marketing and small inaccuracies, some of this makes the most sense of all the computational storage stuff because it tries to not actually be computational storage. And in that context, I wonder what the real value you see of really tightly integrating, instead of saying, okay, I've got my box standard ARM SoC and a couple of VGAs around it. And if it really is that interesting, why do you do a traditional SSD architecture and don't help, say, improving the Linux MTD raw NAND framework, where Linux really does your raw NAND access and its own FPL instead of trying to come up with shoehorn the idea into it when you already have the really raw access. And that MTD framework is, for example, something that will be in your car. If you have any recently modern car, it will be running Linux on raw NAND.
Yep, So I think I'm sure you will correct me if I get this wrong, but I think the question was, okay, this all looks good, but really you're still it's all got the standard NAND paradigm. You're not really taking advantage. If you could change the Linux kernel and access really the raw NAND or do it different.
It's actually right there. Why are we using it?
Okay, so these things exist. Why aren't people doing it? Hey, people could. Why do you think they're not using it? If it's there, we've got lots of these drives. Why aren't people doing it? Well, I'll be very interested. As I say, I think once this comes along, I'm not an expert on Linux. I'm far from it. But I'm from what I do know about it, and I can see, so the NVMe, but there's still some packaging. Are there cleverer things we can do, bits of the stack that you don't actually need if you've just got it in RAM? I think there can be some interesting things that happen. Maybe they're already happening and I just don't know about them. Hello.
How much storage do you normally see on one of these cards?
So yeah, question, how much storage is usually on one of these cards? These are typically enterprise drives. So they've kind of vary, 4 terabytes. You can get smaller ones, but typically in the enterprise kind of space, 4 to 8. I think today NGD said they have 32 terabytes today. So that's a lot of data.
Just a little card like that, right?
Yep, yeah. Typically a U2 or a M.2. Yeah. Now, the challenges here, of course, are always going to be power. Because, and if you've got that much NAND and that much RAM, it takes quite a bit of power. But actually, the compute of an ARM process, depending on how many you've got, but that isn't a huge overhead when you're powering all that NAND and all that RAM. The compute really isn't the huge part of it. So it's interesting. You know, it's because of the smartphones that we've had, where you've had to have very high power efficiency. It's the same processes that go in the storage that, you know, but you've got, yeah, more watts.
So I kind of have this issue all day long. There's a lot of confusion or sloppiness, I guess, between power and energy. Power is sort of a CapEx budget thing for building the device. You can build up to a budget. Maybe when you use it, you have to alternate who gets the available power. That's one. But the green aspect is what the total energy use integrated over time.
Yeah.
Do you address both concerns, or it sounded like there you were primarily talking about power as a staying below a peak in a budget that you have?
Well, part of it is typically whatever you plug your SSD into has a limit of how much power you can draw over that before it starts smoking. So you're right, that is a consideration, and that may well limit, depending on the amount of NAND and RAM that you have in there, limit the amount of processing that you can do. But overall, the energy, though, the fact that you're not shifting all of this data a long way, and that, you know, the green aspects of it, I think are important. You're not having to move it through all these powered boxes that are routing it, networking it, and get more of them to get enough bandwidth as all this data comes on board. So, yeah, if I use the term incorrectly, I apologize.
I wouldn't say you were using it correctly. It's possible to use the term to mean
Yeah.
both, but it was trying to see, and Stephen did the same thing, and Scott kind of does the same thing, and it's something I think we need to be more careful about.
Okay.
Intelligence. Because if you're talking about green, it's the latter, it's energy use.
Yeah.
And I'd like to see some models that actually show that and see whether the energy usage is that to kind of substantiate the claims that you guys are making about flow back and forth across the network. I don't doubt them. I'm looking at models of that stuff myself, but more from the aspect of storage and not
Understood.
so much from the compute and memory and things that are not.
Great. No, I agree. I'd love to see data. It seems to make a lot of sense. I'd love to see data. What we need is our partners with the drives and the people using those drives to generate that data.
It's one of those trust but verify things.
Yeah, but I think, you know, the logic of it. If you're not having to move this data, it costs money to move, costs energy to move this data around the thing. You know, shifting those electrons, it generates heat. You got to then cool it. Also, you know, the big servers just sitting there spinning while they're waiting for data to arrive. That's not ideal either. If they can be doing something more useful, or you need less of them, again, there's a huge power saving there as well, or energy saving.
Down diagonal quicker and spend more time. I mean, if they know what the profiling is going to be,
Yep.
CPUs have pretty good power management.
Yeah.
And can get better. And same thing with, I mean, even like the fiber optic links can shift up and down in their
Yep.
power. So I'm not convinced until I see a more detailed model. As you say, logically it makes sense.
I agree. I'm sure that data will be forthcoming, but yeah, I'd love to see it too. Thank you. Hello.
So if I understand correctly, you mentioned that you're putting Linux kernel inside a drive.
Yep.
So the traditional OS concepts, what kind of changes you think or you're foreseeing about the Linux IO system and maybe specifications and memory management?
So typically, yeah. Oops, sorry. Yeah, no. Yeah, sorry. Yeah, so the question I think was, you know, what needs to change in Linux to get it running on the drive? Is that?
Yeah.
So, I've paraphrased. So Actually, in principle, very, very little. So I'm just trying to think of an example, a good picture that would demonstrate it. Where are we? So for example, if you put an application processor in here, available from many vendors, and you run Linux on there, it's the same as if this were a server. So actually, if you've got a TCP/IP link here, you can be running the NVMe over Fabric TCP protocols on the Linux here. It's a typical server. Now, sometimes vendors like NGD, they do things where they do some tunneling over NVMe to do different things here. So basically, I think if I remember rightly from Scott's talk this morning, there's kind of you map on the files here onto the blocks down here from here, so that nothing changes from the server side. But that was the difference with this is that you've got the Linux running here. What NGDs drive and others today, because it's typically PCIe running over NVMe. So here, when you've got the Linux running here, basically there typically does need to be something that's mapping it on to this system. Where I think this is neat is having the Linux here. Well, actually, because you've got PCIe, you're talking direct NVMe. What's different here is that you're talking TCP/IP to this, and that's why this is kind of more standard Linux.
I'm working on a computational storage for genomics research project at CSD. We're using RT4, but the interesting thing is that we're picking up all the bits directly from Compile. We don't compile anything. So our embedded world is completely off the shelf bits right now.
Okay, excellent. No, I say to me it's a really exciting opportunity. I think for lots of different people, and I think lots of things will come of it that we haven't thought of yet. Of just places where it just makes perfect sense, or by changing software and having the software right at the edge. Yeah, I think it does. It is eco. There are a lot of good things you can do about it, do with it. So good. Sorry, what?
Do you see that you would introduce security problems by running Linux, and would have a whole patch mechanism and all that kind of stuff?
No, it's a very good question. Does this introduce security problems? It introduces, yeah, here, if you're just talking PCIe, the only place they're really going to attack is probably over the debug port that exists on these drives. So more likely than not, this is quite secure. But this is just, ARM, Intel, others, AMD, the security issues around these servers, there will always be holes, but we keep patching them quickly to move along. So it's got the same vulnerabilities as any server. And as long as you can keep patching it by using the standard Linux administration tools, then it's as good as it gets. You can obviously do things to make it more secure. You can have authenticated access. There's things that you can do across the top. But yeah, if you just plug this into the internet, people will come and try and hack it. And some people will probably be able to do it like anybody else's.
That's part of an automated system.
Well, this is obviously inside the hardware itself. There are things like trust zone that keep secure and non-secure, and there's another exception level. But typically, it's really inside the Linux itself that takes advantage of those features to make them secure. But inside your smartphone, it's running Android. It's running it on an ARM system. It's not infallible, but it's pretty secure. The trust zone has been around a long while, and has, there will always be vulnerabilities in any system. Side channel attacks that happened on ARM, as well as and speculation with Spectre and things like that, happened on ARM, happened on Intel, happened on AMD. But then we patch them and we fix it up. So, but yeah, clearly it's more of an attack surface if it's connected to TCP/IP. It's a good way.
In R&D environment, that means you running
Okay. Great. Well, if there are no more questions, well, thank you for your time. Thank you.